I realized that this problem is a little bit complicated, so I've decided to discuss this with you today. So let's first read the problem. A proton is traveling horizontally to the right at 4.5 times 10 to the 6 meters per second. Find the magnitude and direction of the weakest electric field that can bring the proton uniformly to rest over a distance of 3.2 centimeters. And letter B, how much time does it take the proton to stop after entering the field? Okay, so it says in the problem that there is a proton, and I draw this here, that the proton is traveling horizontally to the right at 4.5 10 to the 6 meters per second. And this represents the initial velocity of the proton. But in the problem, it says that we are trying to bring the proton to rest. And not only that, uniformly to rest. So what does that mean? We're trying to slow down the speed of the proton at a constant rate. So every second slows down at the same rate, at the same amount, it is reduced at the same amount of velocity each second, so that when we graph it, if you look at this velocity versus time graph, if this is the initial velocity, 4.5 times 10 to the 6 meters per second, it's going to slow down and it's going to look like a straight line until our final velocity becomes zero. And it's a straight line because that straight line shows that the reduction is uniform. If the reduction of the speed were not uniform, it wouldn't be straight. It be curved, or it will take a different shape. Now, how do we slow down an object's velocity? In other words, how do we make a velocity of an object decelerate? Um, well, if you remember Newton's second law, we can do that by applying a force because according to Isaac Newton, a force causes an object to accelerate, or in our case, to decelerate, slow down until it comes to a stop. So the proton has to experience a force that will slow it down. So my question to you is, if this is the proton and it has an initial velocity to the right, what should the direction of its acceleration be so that it slows down? And the answer to that question is it must experience an acceleration to the right, to the left, I mean, so that it will slow down. And whatever the direction of that acceleration is also the direction of the net force that must act on it. So, in other words, for this object, our proton, to slow down, there must be a force in the opposite direction of its velocity so that it will slow down. These are things that you should have learned from grade 8 or grade 9, but let's just review it anyway. Now, find the magnitude and direction of the weakest electric field that can bring the proton uniformly to rest. So how do we apply a force? That's the next question. How do we apply a force to this charged object? And we know that we must apply a force and it must be in the opposite direction. So how do we do that? Well, we put an electric field and expose it to this electric field, okay, and that electric field will produce a force because that's what electric fields do. We expose it to as weak the minimum amount of electric field that is needed to produce this force, just enough to cause an acceleration to slow down this object. Okay, so actually we already know the answer to half of A. The direction has to be, the direction of the electric field has to be to the left. And that electric field will produce a force which is also to the left on this proton, which is a positive charge. Now, to find the magnitude is a bit more complicated. And actually, by bringing the proton uniformly to rest, we're applying a constant force. The force needs to be constant, not changing. And since the force is constant, that also leads to constant acceleration. Okay? And whenever you have a situation wherein the acceleration of an object is constant, you can actually use the following equations. And the explanation as to why these equations are true are beyond the scope of this activity, but maybe someday I will refresh you or try to derive these equations. But whenever you have a situation where an object is constantly accelerating, or in this case, constantly decelerating until it comes to a stop, then you can use the following equations. V final equals V initial plus that constant acceleration times time. And there's another formula. These are called kinematic equations. V final squared is equal to V initial squared plus 2 times acceleration times, let's call this delta x, or the displacement of the object. Or if it's a straight line motion, then it's equivalent to the distance. If it's just one-way straight line direction, like this problem. And you can also use the formula, again, the displacement is equal to initial velocity times time plus 1 of at squared. These are kinematic equations, and they can be applied to your problems if and only if the acceleration is constant. Again, our force that we apply is constant because the clue is we are trying to bring the proton uniformly to rest. So we're trying to get it to slow down at a constant rate so that it stops. And to get it to slow down at a constant rate, we need a constant force, which leads to when a force is constant, the acceleration is also constant. And since the acceleration of this um, object is constant, we can use these equations. And which equation should we use? It depends on the given. Are we given the final velocity? Because we're looking for the direction of the electric field. Now, in order to get the electric field, we need to know the force first. And in order to get the force, we need to get the acceleration force first. So why is that? Because we know that acceleration is related to the force by A equals Fm. And we know that the force is related to the electric field by this equation for test charges. And this proton is considered a test charge because it's the one exposed to the electric field. So I hope you get the idea that in order to get the answer to letter A, which is the electric field, we first need to get the force. But in order to get the force, first need to get the acceleration. Okay, so let's get the acceleration. Our VF is given to be 0 because we're bringing the object to rest. We also have our initial velocity, which is 4.5 times 10 to the 6 meters per second. What else are we given? This distance of 3.2 centimeters, that's actually our delta x. 3.2 centimeters centis times 10 to the negative 2. Okay. And we're looking for A. I guess that's the only thing that's given. Now we have VF, VI, delta x, and A. And there is no other formula that can hold all these variables except the second formula. We don't have the time, so we'll choose a formula that doesn't have time. And it's this second formula. So VF squared is equal to VI squared plus 2A delta x. But we're looking for A, so let's derive A. So I'm going to bring VI squared to the left side, and then I will divide all by 2 times delta x. And I hope you know how to do this, but this is our final equation for A. Okay. Our velocity final is 0. Our initial velocity is 4.5 times 10 to the 6 meters per second. And we square that. And our displacement is 3.2 times 10 to the negative 2 meters. Once you manipulate this, you will get a negative value, which makes sense. Our object is moving to the right with a positive velocity because it's moving to the right. And we expect that the acceleration must be to the left because we want the object to slow down. And since the acceleration is to the left, it must hold a negative sign. So I actually need my calculator. Good thing I have one in my cell phone. 4.5 times 10 to the 6. No, I don't. So let's just do 4.5 times 4.5 divided by 6.4. So I'm getting 3.16 times 10 to the 14 meters per second squared. Now I need to get the electric field, but first I need to get the electric force. So the electric force is just the mass times the acceleration. And we all know that the mass of a proton, you do your research, it's 1.67 times 10 to the negative 27 kilograms. Kind of memorize that. You will too in the future. And this is taking so much time. The answer is 3.16 times 1.67, 3.16 times 1.67 is equal to 5.27, 5.28 sorry, 5.28, well, times 10 to the negative 13. So that's our force. But to get the electric field, we need to divide that. It's a long process, right? Force divided by the charge of a proton. It's a negative, of course. And the charge of a proton is 1.6 times 10 to the negative 19. Same as the charge of an electron, except it's positive. And I hope we get this answer because I just impromptu this thing. 5.28 divided by 1.6, 3.3. We actually got the correct answer. So happy. 3.3 times 10 to the 6. If you have time, try to answer this problem. Okay, goodbye.